talk about accessing persistent memory from Java. And first, I guess, a little bit of motivation why it's worth putting effort into Java particularly. It's very common implementation language in the data center. And I've made a list of, just the Apache projects that came to mind that are all implemented in Java. And all of these almost all of them are focused on providing, data storage or data manipulation. So for things like persistent memory, they're relevant. This is the high-level view of what's currently available or in progress for accessing persistent memory from Java. The first couple bullets talk about volatile use of persistent memory. This was.
I'm gonna have you switch. It's a little. You're getting a lot of feedback, so
okay.
Do this one and maybe give me your other one.
I don't have one. That's maybe what the problem.
Okay, you're gonna speak from the front end. So we'll do it from from number 3. Okay,
this one.
That.
Okay, is that good? So the first couple of bullets here talk about accessing persistent memory from Java in a volatile use case, not trying to recover the memory after a restart. And the first one is an extension to the Java virtual machine. On a command line, you specify that you would like all of the Java heap, that is the memory that stores Java objects, to be on persistent memory. So other than that, there's no code changes. And the second one is an extension to that, which allows you to, split that heap into the garbage collector's 2 generations, old gen and new generation, so that long-lived objects live on persistent memory, but the fast churn rate young objects remain on DRAM. So both of these are finished. The first one is available in Java 10, and the second one will be available in Java 12 coming up. The second set of bullets is libraries or extensions to Java that allow both persistent and volatile use. The first one is a proposal by Red Hat, which takes a common Java class, a mapped byte buffer, and extends it to allow you to map persistent memory. And really the only change there is a force method on the buffer, which forces media out to disk, is now capable of forcing cache contents out to persistent memory. So anything that worked with byte buffers will work with persistent memory. That's a really good idea. And then Intel has developed 2 libraries, the low-level persistence library and the persistent collections for Java library. They're both available on GitHub. They're both still in active development. And I'll talk about one of them and some application code we've written using it in subsequent slides. So here's the 2 Java libraries we've put up on GitHub for Java. They really represent sort of the extremes in access to persistent memory. One is extremely low level. It's blocks of memory, unstructured bytes, and you're able to just set those bytes and read those bytes. That's LLPL. And persistent collections for Java is just the opposite. It's high-level Java objects that reside on persistent memory, and other than that, they behave like Java objects. You can see some of the properties that are different here. In particular, one is manually memory managed, LLPL, and the other is garbage collected. Thank you. And in general, the low-level library offers very little in the way of like thread safety or forced kinds of checking. And so you can build your own abstractions out of it. And in fact, the persistent collections library was built out of a very low-level layer that we built similar to LLPL. So by offering this low level and this high level, we hope we can capture a lot of the Java development community. A little bit more detail on the low-level library. There's really just 3 parts to it. One is a heap API for allocating blocks of memory. And the memory block API, which is just a low-level accessor, lets you read and write Java integer types and copy bytes between blocks in persistent memory or between Java DRAM memory and persistent memory. One of the things we discovered through application development is that there's a wide variety of data consistency policies you might want to implement, data integrity policies, either expensive and appropriate for mission-critical use, or much less expensive and suitable for controlled exit kinds of processing. So in the face of failure, you might throw the memory away. In support of that range of consistency schemes, we offer 3 different kinds of heaps. The API is very similar, but they have different semantics to them. Transactional heap makes sure that everything is fail-safe. All the writes are fail-safe and will roll back on interruption. And then 2 lesser, lower strength kinds of consistency promises. A persistent heap will ensure that it's all durable, all the writes are durable. And then this plain heap lets you do just about anything and build, in fact, the other 2 kinds if you wanted to out of it. And it's very suitable for volatile use as well. So just pure reads and writes to cache-coherent memory. We'll show a little bit of examples for the transactional heap, which we use in some Cassandra code that we've worked on, that Andy mentioned. The last part is there is a transaction API, and this is to allow users to group already transactional operations into an atomic whole. So if you need to do a bunch of things as part of an operation and they all need to go forward or roll back together, it's easy to use this API. This is probably very small in the back. I'm going to skip the 2 sample code slides here. I wanted to have the detail in here. This is LLPL code doing some simple writes and then recovery after a restart. And you can look at them in a copy of the slides. So we had this topic come up, and that is which of these open source projects would be a good candidate for retrofitting with persistent memory. And Cassandra, one of the projects listed on the first slide, is widely deployed, and it's popular enough where if we were to do a complete replacement of the disk with persistent memory, it represents a possible max upside for performance and maybe even simplicity. So it starts life with this log-structured merge tree, which is a 2-level kind of data structure. Part of it is in DRAM, and then when that fills up, it gets flushed to disk, and that flushing happens to an immutable file. And then those files eventually get compacted. So it's a very well-known database kind of structure, and that was our starting point. A little bit of detail on what the read and write path in Cassandra look like and how we changed them. The write path in baseline Cassandra takes the write request, and writes it to a commit log. And then it's written to this top-level DRAM layer of storage, which is a sorted table. It's a Java sorted map. And when that thing fills up, it flushes to this SS table, which is the immutable files I mentioned. So there's not too much complexity here, but it is a multi-step process, and there is significant structure above the persistent memory, or the persistent layer, and below. In our changes, we got rid of the log-structured merge tree. The commit log goes away, that DRAM buffer, the write buffer, goes away, and we just write synchronously to a mutable store in persistent memory. The read path is a highly optimized, this is the original Cassandra read path. This is a highly optimized thing. A lot of data in volatile DRAM in order to give you high performance location of the right bytes to read and write in the persistent layer. So there was an additional opportunity here to simplify this stack. And it looks very similar. We're synchronously writing, or synchronously reading from a mutable store in persistent memory. This was one of the big risks, and we didn't make it ourselves. We got some help from the Cassandra open source community, before we even tried this. And it sounded plausible, so we went forward with it. This is the stack we ended up with. And I don't know if you can read the text back there, but I'll just utter the layers here. The top one is a very important piece. The green box is a pluggable storage API for the Cassandra database. That is, we implement a module, it implements a standard API, and we can have both disk and persistent memory backends for the database. The blue box is our persistent memory implementation of that modular backend. And the only additional dependency that we have in this Cassandra engine is it depends on this LLPL library, on this open source library. In turn, I'll point out that below the Java VM layer, and this operates on JDK 8 or later, we depend on persistent memory development kit, in particular for the hardest parts of accessing persistent memory in my mind, which is memory allocation and transaction support. And that's all heavy lifting that we get for free. So this is that pluggable storage engine API in a diagrammatic form. The front end of Cassandra, the processing of requests, and a pool of reader and writer threads that actually submit the work to a storage layer is unchanged. And this dotted box around each one of these modules below would represent that API. And you could have a disk API that implements this and a persistent memory instance that implements that API. In particular, this pluggable storage engine API is designed to be applied at a granularity that is not all or nothing. You could have certain database tables that you needed high response from, really low latency and critical data, and other tables that were less critical. So you could actually not only deploy alternate storage engine technology, you could deploy a mixture of them at the table granularity. We've implemented that middle box, and I'll dive into the details of that in the next slide. I should point out, this is the second, we implemented two persistent memory storage engines. The first one used the high-level library I pointed out called persistent collections for Java, and we just used generic persistent collections from that library to implement the data structures for the storage engine. It worked very well, it was very functional, and the read performance was particularly good, and that got a lot of interest of some members of the Cassandra open source community. At that point, one of them really, what's called I call it an Uber committer. It's a committee that decides the direction that Cassandra goes in. Came up with a design, an alternate design to our engine, and you're looking at it here essentially. And this is how a Cassandra expert would design a persistent memory storage engine. So we jumped on this and implemented it. And I can tell you it worked out very well. I'll describe a little bit of what's in the box here. Cassandra takes the data that's submitted to a cluster, and it distributes all that data across the cluster using a hashing scheme, a thing called the murmur3 hash, and it distributes partitions of the data out to different nodes of the cluster. This is showing an engine on a single node, but it uses the same distributed scheme, and in fact the same murmur3 hash to distribute data within the node across shards in a single instance of the storage engine. And the reason this is so wonderful is that all the data structures below those queues are all single-threaded. And so we have multi-threaded submissions into these queues, and there's some contention there. But once it gets into the queues, they're both serialized, and we have all the benefits of non-contended access to portions of persistent memory. Each one of the triangles there is a data structure called an adaptive radix tree. And this is another real success. We've implemented a number of collection classes in Java for persistent memory with some very good success, but this one is particularly suited for this kind of an application because radix trees are wonderful in that they have a large branching factor. You can store a lot of data without having a lot of footprint. But when they're sparsely populated, they have a lot of waste, a lot of pointers to empty child nodes. So this adaptive one sort of works through that problem and gives the best of both worlds. You have a maximum branching factor of 256, but when it's sparsely populated, it uses smaller nodes, and so you don't have the footprint problem. We implemented that from the paper, and this was part of the suggested design from the Cassandra open source community, in a two-layer cascade. So you ask for a partition, which is a group of rows, and you'll get back an instance of one of these trees. And then you query that tree, and you ask for one of the rows within there, and you'll get back one of the rows at the bottom. So it's really no more complex than that. It was a lot of work to implement the first time, but it's a very simple and elegant design. This particular implementation offers 3 benefits performance-wise. We have a much simpler code path here, and so we see a dramatic reduction in instructions per operation, so-called path length. We also get great scaling. This sharded design gives us the ability to apply a lot of cores to a single instance of the engine, and so we see a great CPU utilization out of this. And because it's just loads and stores to memory, as opposed to all sorts of other high latency kinds of operations, we have this good efficiency in cycles per instruction. And it's not only lower than it would be going to disk, but it's very predictable. So achieving SLAs of a particular level, it's very well behaved. Sometimes you push something too hard and it really gets slow. We don't see that. We see sort of a graceful degradation of performance. Anyhow, that's the success story, I think, for persistent memory in a real-world application. And we've submitted this to the open source. We're working to get it upstreamed. There's a lot of work to do that, but this is all in the open source, and the links are in the deck here. So overall, I think there's just 3 takeaways. Having libraries such as PMDK and LLPL right now lets you dive into this application-specific use of persistent memory, changing your code and getting performance benefits that are hard to get any other way. We see over 8x gains in read rate with Cassandra from this implementation. The second thing is, I think this modularity is really important because people don't want to go all or nothing with persistent memory, I think. And so having modular APIs, pluggable APIs, to let existing products and even new products support multiple kinds of media, it's really another kind of success story, and I think important for the future of persistent memory. And I think it's a really good success. I'm not sure how much more work is left to getting into upstreamed and fully supported, but from a technical standpoint, it's a really nice design, and it produces great results. That's all I had today. Anytime.
We do have a few minutes for some Q&A on that. I think a very good example of dealing with applications, existing applications, that can be simplified. I think hopefully you all got that message. Actually making things simpler turns out to be really effective. So any questions for Steve? Ron, here in the front. We'll get you a mic, Ron.
Ron Dennison, Research Development Consultants. Can you quantify the kind of performance improvement you typically saw?
Yeah, I'm going to look around the room because Intel's has a very well-defined process for publishing any kind of performance numbers. So I have them in my head, but I'm going to look over here. I've already mentioned one because I think it's been publicly announced. We see over 8x throughput gain at a similar SLA, at an exact same SLA in the read rate. And I think you could get a good chunk of that just by using persistent memory in a no-code change way. But that second big chunk of it comes from those code changes you saw in the simplification. So it's a two-forked opportunity here.
Very good. Other questions? Over on the side, right over there, Marty.
This one I'll give
What's that?
I'll get this one.
Okay, this one, and then you're next.
So,
We got time.
One of the things Cassandra does is garbage collection. So it compacts the data that you have freed.
Yeah.
Right. So you didn't talk about that because that is usually the bottleneck in most databases.
Yeah, the garbage collection, I mean, there's no compaction in our storage engine. It's a mutable storage engine. So when we do a merge or we do an update, it's an overwrite. You're writing over the top of mutable data. And in fact, we use exactly the same merge code that the baseline Cassandra does. We use the same serialization code. So there's a lot of code reuse there, but it's a completely different mutability story, and therefore the notion of garbage collection compaction, I think, it doesn't exist.
Even if you're overwriting, if the object size changes, you cannot overwrite it in place. So
We
you
do.
would have garbage, you would have fragmentation. How do you deal with that?
Yeah, fragmentation is a hazard in any of this sort of allocate and freeze. But when we do write, we write right over the top. So what we do is if the data fits in the existing allocated memory, we overwrite it. And if it doesn't, we allocate new memory and free the old. And that's where fragmentation, which is not a new problem, has to be addressed. And we do that with things like slab-based allocation and some other tricks in LLPL.
So fragmentation and memory allocation has been a hard problem to solve in the memory world, in the volatile memory world. So you think it's even probably harder with this approach, don't you think so? So do you think that will come to bite us down the line?
It's a really great topic, and I think at the point you offer like stable values like pointers or offsets, you open the door for fragmentation. But in PCJ, we never offer that, for example. So there's a choice to be made in the API, what you offer to developers. And if you were to offer copies of data, if you had a KV store, for example, then the fragmentation can be managed by moving data around in the library. In this case, it's true. We offer stable values for those memory blocks in LLPL, so we can't move them on people. But it's an important topic, and it's not impossible to solve. It's just that we made one choice right now, and we might want to change some of that going forward.
Okay, the question on the other side, and then we'll move ahead to the next session. Microphone coming around.
It's all right now, we're tapings.
I worry this might be above your pay grade anyway, but there was a question that got asked earlier, which is what does a key value store look like if you start with persistent memory and build fresh and new as opposed to just improving or upgrading Cassandra? And if you take that model that you've got, is that it, or is there some next layer that we can get to with it, and where is that in the programming model?
Next layer for easier use or something?
Yeah, or just key value store, persistent memory native could never run on anything
I think
else.
the big question is language integration there. I mean, we can build a library that offers a service, a data service like key value store. We could also offer persistent Java objects so that you simply write your code like you would in Java, where you have fields, but those fields can be persistent. And our persistent collections for Java library does that. It does it as a library, so it's a bit non-idiomatic. But we start with low-level things like memory blocks and structs, and we go to a key value store like a data service that's sort of in the middle. And at the high level, we could do deeper language integration so that people are doing idiomatic programming, memory-based programming like they've always done in their languages, but now they have the choice of recovering those structs or objects after a restart. I mean, it is a wide open world, so we're still exploring it.
Yep. Very good. Let's give the speaker a hand again. Thank you.